Hey everyone, as promised, I'm putting together a quick presentation. Well, I don't know how quick it's going to be actually, but it's a quick presentation, I hope, about z-scores and p-values. Both of these are fairly complex, but yet really important things to know. So we'll go through z-scores first, and then I will talk a little bit about p-values. Z-score. Z-score is a method of normalization. So what does that mean? And that's why I've got the there, because there's some work to be done to sort of understand normalization, and we'll talk about that in a bit. I'll go through a couple slide or two that talks about why do we need to do it and how do we do it. So why do we normalize the z-scores? Well, that's best explained by giving you a scenario. Let's imagine that we have two variables and that we're a company called Zillow. What Zillow does is Zillow actually takes in a number of variables and determines projected house prices. But we're going to reduce this down for simplicity's sake to just one variable. And that one variable is going to be the square footage in a house. So we're going to take that square footage in a house and we're going to use it to predict what the likely house price would be in that particular market. So when we look at our variables, we notice that the range of values for both variables is vastly different. So let's imagine that our square feet is between 800 and 5,000 square feet and that our price range runs from 250,000 to 2.25 million. That's a really big difference. And if we were to do even a correlation or some other tests that look at these two numbers and compare these two numbers, we might get kind of odd results because vastly different ranges can often throw off the accuracy of many statistical tests. So what we're going to do instead is we're going to convert the values to z-scores. Now how do we do that? Converting the value to z-scores means that we first calculate the mean, and you can use your equals average function in Excel to do that. And then you calculate the standard deviation. You can either calculate the standard deviation using the stdev.s for the sample or the stdev.p for the population. In most cases, we'll probably be working with a sample, so you'll use the first standard deviation function. Once we have those two values, we take the third value, which is the raw score, and we can convert that to z-score. So first thing we do is we subtract the mean from the actual value. That's the value that we've pulled out, some actual value. Some of those are going to be positive and some of those are going to be negative. And if you think about it, that makes sense because the mean is actually in the middle of these numbers. And so when you subtract the mean, sometimes the number will be bigger and sometimes the number will be smaller, resulting in positive and negative values. Then we're going to divide that difference by the standard deviation. And that is your z-score. Again, you'll get some positive z-scores and some negative z-scores. But by converting to z-scores, it puts both ranges on a similar scale. And now we're not really measuring square feet or prices. We're measuring the distance from the respective means in both of those sets, both of those lists of numbers. Here's the first example. If you look at the left-hand column contains my raw values or my actual values. My mean for those values is 13.88 and my standard deviation is 4.389517. I take my mean and put it in the second column and subtract it from my actual values and get the difference. Again, some of those are positive and some of those are negative. Depends on the size of the actual value relative to the mean. Then I divide each one of those values in the third column by the standard deviation. And so when I divide by the standard deviation, I get numbers that fall into a range, usually never exceed positive 3 or negative 3. Okay, so that's one example. Let's look at another example. Now my initial numbers are far higher. They're in the thousands. And so I have a way different range, completely different range. And if I were to compare this to my first set of numbers, they would be vastly different. If I go through and I calculate the mean here, I get 13,875, and my standard deviation is 4389.517. I take my mean and put it in the second column, subtract it from all of my original values, and I get some negative and some positive differences. I divide those differences by the standard deviation, and I get my z-scores. And these z-scores look very similar to the z-score scale that we saw before. In fact, if you look at them side by side, I did this on purpose. You look at them side by side, these numbers that are so much smaller than these numbers generate exactly the same z-scores as each other. And that's because of their scale and their distance from the mean. Now that we know that, we can learn a little bit about how we can use z-scores. Okay? So let's imagine that we're taking a look at a normal distribution. That's a bell-shaped curve. And we have a bell-shaped curve with, in the dead center is the mean value. And we have 50% of our values that are higher than the mean and 50% of our values that are lower than the mean. The z-score can tell us a lot about that normal distribution. First things first, it can tell us how many scores or how many values we're actually dealing with in a particular section of the bell-shaped curve or the normal distribution. As an example, the distance from the mean to a z-score or a standard deviation of +1 accounts for 34% of all of the values that you have in your normal distribution or your bell-shaped curve. That could be 100 values, that could be 10,000 values. But the way that a normal distribution works is that when you have the distance between the mean to z-score of 1 or a standard deviation of 1, you have accounted for 34% of all possible values in that data set. Likewise, on the other side, the distance from the mean to -1 accounts for an additional 34% of all values in the bell-shaped curve. So together, if you're ranging from -1, standard deviation or z-score of -1, and a standard deviation or z-score of +1, you're accounting for more than 68% of all values in your data set. Okay? This will become important later. If you go from -2 to +2, that's 2 standard deviations or 2 z-scores, well, z-score of 2 I should say, -2 to +2, then you're accounting for 95% of all of your data points in your data set. And you're accounting for greater than 99, somewhere around 99.7 of all of the data points in your data set if you're ranging from -3 to +3. Why is this important? Well, we can use that information to determine probability. And what we're determining with probability is we're determining the probability or the percentage of scores that are higher and lower than any selected score in our data set. So knowing a raw score, that's a raw score, that's just we're pulling one member of our data set out, we can calculate its relative probability. We convert the raw score to a z-score. Remember, we subtract the mean and divide by the standard deviation. Then we look it up in the z-score table, and I will show you the z-score table, but if you want to look at the z-score table, it is in your book at the end. It is Appendix 1B. And we get the area between the mean and the z-score, and that's really important. The area between the mean and the z-score is going to help us determine our probability. We can't forget the other side. That accounts for the other 50%. So imagine for a second that I am looking at a z-score of 1. I want to look at the probability or the percentage of scores that are between the mean and z-score of 1. And we've already determined that that's 34%. We looked at that in the previous slide. It said it was 34%. Okay, so that doesn't tell me really much by itself, but if I add the 50% that's on the other side of the mean, then it tells me that at that particular point, 84% of my values are either higher or lower, and 16% of my values are on the other side. Okay? That gives me a relative probability of where my data points lie. So what we can determine is we can determine the probability of getting a higher score than the one I selected, and the probability of getting a lower score than the one I selected. Let's look at an example. Let's imagine that I have a data set of 5,000 points, and the mean is 75, and my standard deviation is 5. And out of those 5,000 points, I pull a single record. Maybe it's a record of interest, or it has some sort of significance for me. And it turns out that its raw score on this particular scale is 82. With a score of 82, I will subtract 75, which will give me my difference, and I'll divide by the standard deviation, and that will give me a z-score of 1.4. What I'm going to do is I'm going to look it up in the table. And what I'm going to look for is I'm going to look for something that shows me the distance between the mean and a z-score of 1 point. This should say 1.4, not 1.5, because I was looking at 1.4 up here and I just typed it wrong here. So a score of 1.4. And when I look that up in the table, it says 41.92 is the value. That means that the percentage of data points that are accounted for between the mean and 1.4 standard deviations, or a z-score of 1.4, is 41.92. That's 41.92% of all of the values in my data set are in that range. Now I'm on the positive side, so I'm on the right side of the curve. So now I have to also think about the 50% that are on the left side of the curve, and I just throw that 50% in there. That comes from the other side. The probability of getting a score in my data set less than 82 is 91.92 because I added 41.92 to 50, I got 91.92. So 82 is a relatively high score with 91.92% of my scores lower than 82. But on the other side, the probability of getting a score in my data more than 82 is pretty low. It's about 8%. So about 8% of the scores are higher than 82, and about 91% of the scores are lower than 82. Let's take a quick look at that table, if I can find it. Maybe I don't have it. Bear with me for a second here. Hopefully you're seeing this. Here's the table that I'm referring to on page 413 of your textbook. And here's how it works. Remember, I had a z-score of 1.4. And the way that they've arranged the Salkin text is different than most z-score tables. But since this is the table that you have, I want you to be able to see it. So my z-score of 1.4 is going to be over here in the ones. And actually, if I go all the way down, 1.32, I have to go to the second page. And the second page shows me 1.33, 1.34, all the way down to a z-score of 1.4. Z-score of 1.4, I look over here, 41.92 is the area between the mean and that particular z-score. That's where I got the 41.92. Okay, we'll come back to this example in a second, but for now I want to go on to our second example. We just checked the z-score table, so there was a slide there to remind me to do that. Okay, what do we mean by the other side? I already explained this, but I'll explain it again. Remember, our z-score was going to be 1.4, and this scale is a little off, but imagine for a second that the z-score was actually right here, 1.4. And the distance between the mean and that 1.4, as the table just showed us, is 41.92. But we stopped at the 0 point of the table, and we want to determine, in our distribution of all of our data points, we want to determine the percentage that are lower than a z-score of 1.4. So we have to add this section, which is 41.92, to this section, which is 50% of our data points, and that's where we got the 91.92. This is example number 2. The mean is 30, the standard deviation is 4, the raw score I've selected for whatever record of interest I have is 18. That's quite a bit lower than my mean. With a standard deviation of 4, I can see that that's going to be quite a ways away. So I calculate my z-score. I take the value of interest, subtract the mean, and divide it by the standard deviation, and it gives me a z-score of -3. So we can look this up in the table, and then we can, again, we don't want to forget about the other side. So let's go ahead and go back to our table. And if we look at our table, we're going for a z-score of 3.0. We've got to go back up to the top because the z-score of 3.0 is all the way over here. And it tells us the area between the mean and that z-score is 49.87. Okay, so we'll go back to our slides. And if we go back to our slides, we'll see that if we add the 50% to the 49.87, the probability of getting a raw score higher than 18 is 90.9987, or the chance is 99.87. And the probability of getting a raw score lower than 18 is 0.0013. So that means that we have a very tiny, minuscule probability of getting something that is lower than 18. And we have a very, getting a raw score that's lower than 18, yes. And we have a very high chance of getting a raw score that is going to be higher than 18. It gives us our placement on the curve or the normal distribution and tells us where things lie and where we are relative to all the other data points. Now let's talk a little bit about p-values. Okay, on to p-values. So a p-value is probably one of the more critical things you're going to need to know, whether you're going to do a study that is quantitative or whether you're going to do a study that is qualitative. And for all you qualitative people who are thinking, I don't need to know this stuff, let me tell you that you do. And the reason why is because when you do your lit reviews or you start looking at other articles or you start kind of building on the research of others, a lot of that's going to involve quantitative work that involves p-values. So it's really important that you understand what a p-value is. A p-value is a probability value. And it's really, what is the chance that I got my result purely by chance? If you flip a coin, you have a 1 in 2 chance of getting heads, that is not significant. It's a chance. It's purely by chance. There's really no structure to that at all. Same thing if you roll a die. It's 1 in 6. That's still a very, very not significant way of being able to determine why you got the result you got. A p-value is truly and really an indicator of significance, and it's statistical significance when you're testing your alternative hypothesis. And we'll talk about this over and over again because I want to make sure you really truly understand it. What we do is we state a null hypothesis, and generally we state a null hypothesis for stating that there's no relationship between a set of variables, or there's no whatever. Then we test, or we state an alternative hypothesis that says we think there is a relationship. Then we conduct whatever statistical test we want to conduct. And in this particular set of slides, I'm using correlation coefficients. But you could do ANOVA, you could do logistic regression, you could do a whole other set of tests that you would want to do. And a p-value will always be provided. And what the p-value is a derived value that tells you how significant your result is. And what it's really truly stating is, when you run your test of your alternative or research hypothesis, what is the chance that you would have gotten the result you got if your null hypothesis was true? Let's think about this for a second. I'll go through it again and again with you. Think about running a correlation coefficient. And we get a correlation coefficient which, as you know, ranges from -1 to +1, with positives being that there's a positive relationship and negatives being that there's a negative relationship between two variables. So imagine that we get a correlation coefficient of 0.8. That means that when one variable goes up, the other one mostly goes up. And that's a pretty strong correlation coefficient, right? And we're testing our alternative hypothesis. We're testing that there is a relationship. But there's that null hypothesis still sticking out there saying, nope, there's not a relationship. So if we get a result of 0.8, that tells us that we think there's a relationship, but the p-value is what really tells us if the relationship is significant or not. And there are a number of factors that can make something not significant. It could be the number of data points. It could be the way that the data points are arranged. It could be the way that the test was run. But what we're saying is, did I get my 0.8 correlation coefficient? Am I able to get that? What's the chance that I am able to get that if there's no relationship between these data points? If my null hypothesis is true. That is what your p-value is telling you. Okay? Thus, because of that, you want the smallest p-values possible. So in our example of the 0.8 correlation coefficient, you would have, or you would want to get a p-value of less than 0.05 or 0.01 or even lower. The lower the p-value, the lower the chance that you got the result when you ran the test of your alternative hypothesis if the null hypothesis was true. Okay? Again, we'll go through this in a lot more detail. All right, one thing that's important for you to understand is that you, the researcher, you decide what the p-value of significance is going to be. And we call this the significance threshold. You decide what that's going to be. 0.05 is the most common. And what that is stating is that there's a 0.05 probability or less, which can also be as a 5% chance, that you got your results purely by chance, that there's no significance between my variables. Really what this is saying is that there's a 5% chance or 0.05 probability that you got your results when the null hypothesis that there's no significance between your variables is true. Okay. So by setting that 0.05, it means that I am only going to accept those results where there's less than a 5% chance that I got an erroneous result. Sometimes in the sciences, or when we really need to be very, very precise, the p-value can be set to 0.01. And that basically means that there is a 0.01 probability or a 1% chance that I got my results purely by chance, even when my null hypothesis is true. So p-value is typically noted as a p is less than 0.05, or a p is less than or equal to 0.05, or even when you know the exact value when it's returned from statistical software, you can get a p that is an actual value. P equals 0.05. P-values are everywhere. Almost every statistical test uses them. They show the probability of getting result. Again, I'm going to stress this again. Important. The p-value is the probability of getting a test result from your alternative hypothesis if your null hypothesis is true. Okay? So if I set my p-value threshold to 0.05, that means I am only willing to reject my null hypothesis that there's no relationship if the p-value from my alternative test gives me the value that is less than 0.05. That means that there's less than a 5% chance that the results I got were purely by chance. And it means that the probability that I got the result I got if my null hypothesis was true. More on p-values. Let's use an example. Okay, hypothesis, my null hypothesis. There is no relationship between response rates and average scores in course evaluations. So bringing this kind of near and dear, many of us are educators, and many of us implement course evaluations at the end of quarters or at the end of school years. And so we're going to run a test. And our hypothesis actually is that there's a relationship between response rates and the average scores in a course evaluation. Meaning we believe that the higher the response rate, the higher the average score in the course evaluation. Our null hypothesis says no, there's no relationship between those two things. Okay? So we're going to go ahead and set our p-value threshold to 0.05, meaning that we're willing to accept a 5% chance that the results we get are basically wrong. So I run my test of my alternate hypothesis. So I check to see if there is a relationship between response rates and average scores. And I get a correlation. My correlation value is 0.52. But I get a p-value of 0.111. What does that tell me? That tells me that I am not able to reject my null hypothesis. I'm not able to reject my null hypothesis because 0.111 is greater than 0.05, meaning that I have not met my threshold. I have exceeded my threshold. So my statement that I was willing to accept a 5% chance that my results were wrong and a 95% chance that they were right was exceeded. And in fact, what I got is an 11.1% chance that my results were wrong, and that's just too high. I'm not willing to accept that. So I do not reject my null hypothesis, and consequently, I cannot accept my alternative hypothesis. What about these? We got a correlation coefficient of 0.58 and a p-value of 0.021. Well, that's looking a little better. It's less than 0.05. If I set my threshold to 0.05, I can reject my null hypothesis because the p-value falls below my threshold, and so I believe there is a relationship. There's still a 2.1% chance that I'm wrong, that the results I got were purely by chance, but that's low enough. That means that there's basically a 98% chance that I'm right, and so I'm going to go with it. If I get a correlation coefficient of 0.84, but my p-value is 0.311, that's a 31% chance that my value or my results are wrong, that they're purely by chance and they're kind of wrong and that there really is no relationship between those variables. So I fail to reject my null hypothesis on that one. Lots of times you'll see results where you'll get a correlation coefficient or some other statistical result, and you'll get a p that only goes out to so many digits, and it's 0.000. If you keep going, maybe several digits later, you'll hit something other than a 0, and that is an extraordinarily low p-value, and those happen quite frequently. And that means that you can have a great deal of confidence in your result, and you can firmly reject your null hypothesis and state that your alternative hypothesis does have some validity. If you see a very low correlation coefficient, 0.12, and your p-value is good, 0.001, that means you have significance, right? That means in that case you have significance. It's a significant result. You can reject your null hypothesis, but your result may not be meaningful. And we're not going to talk a lot about that today. We'll just focus on the p-values, but just know that you can get a significant result indicating that you can reject your null hypothesis on a result, doesn't happen very often, but on a result that is really not meaningful because a correlation of 0.12 is pretty small. So at a 0.05 threshold, we can reject the null hypothesis for 1, 3, and 4. At a 0.01 threshold, we can only reject the null hypothesis for 3 and 4 because only those two fall below that threshold. Okay, why do we pick 0.05 over 0.01? Most times a 5% chance that we got the results purely by chance is good enough. And we do that because we're kind of walking a tight line here. We want to make sure that we're trying to get a fairly trustworthy result, but the lower we reduce the p-value, the more likely we are to cause an error where we state that there isn't something there that there really is, and that's called a type 2 error. I'm not going to go, the book goes into type 1 and type 2 errors. I'm not going to go into those right now, but we would basically get a false negative. If we select 0.01 as our threshold, we say that we will reject the null only when there's a 1% chance or less that our results were by chance. And that's really restrictive. So imagine that could eliminate quite a lot of significant results. So think about this. When you're setting a p-value that is less than or equal to 0.01, you're saying that you would be willing to rule out a test that has a 2% chance of being wrong. and a 98% chance of being right. That's a little bit simplified, but let's just work with it now. And that you don't want to do that. And you don't want to throw out something that has a 98% chance of being right, because you will get a lot of false negatives. Sometimes that's right. Like I said, a lot of times in the sciences, they really need to be very, very precise. So they will set a p-value threshold that is very restrictive, but quite often that's too restrictive. And rejecting the null hypothesis. Why do we say we reject the null hypothesis and not that we accept the null hypothesis? Because rejecting the null hypothesis, remember the null hypothesis, first of all, is that there is no relationship. And so we select our p-value threshold, and then we run our test to test our alternative hypothesis. Remember, we're looking at whether or not there's a relationship. We get our results, r equals 0.73 and a p-value of 0.04. We ask ourselves, what is the chance I could have gotten these results if my null hypothesis is true? That's about 4%. Is that good enough? And we reject the null and embrace the research. That's kind of a summary of what I've been talking about all along. This is what I was thinking I was talking about. Why do we say fail to reject instead of the fact that we would accept the null? Because failing to reject the null does not make the null true. Remember, there's a percentage there. We're failing to reject it. We're failing to say that it's false. But we can't just say, because it's not false, it is true. It could still be false. There's still a percentage of a chance that it could be false. So we are not going to blindly and totally accept the fact that it is true. We are only going to say that we are failing to reject it. It just means that there's too much of a chance, too high of a p-value, that the result we got when testing our research hypothesis was true with our null hypothesis. Even our null hypothesis could be with our null hypothesis in place. So in this case, there's too high of a chance that there really is no relationship between the variables being tested. If we have an example of a test where a correlation coefficient is 0.14 and a p-value is 0.34, that means that there's a 34% probability, or 0.34 probability, or a 34% chance that I got this result even if the null is true, and that's pretty high. And that's entirely possible. The null could be high. There could be no relationship between those variables at all. It's still going to throw you a correlation of 0.14, but with a p-value of 0.34, it's a pretty high chance that it was purely by chance. So we failed to reject the null because my test did not reach my threshold. Okay, that was long. I stuttered a little bit over the words, but hopefully you get the point. We are looking at z-scores for normalization. And z-scores allow us to determine for a particular value the percentage of scores that are higher or the percentage of scores that are lower. And then our p-value is our threshold that we have stated that if our values that come from the test of the alternative hypothesis, if they fall below the p-value, then we can reject the null and accept the alternative hypothesis. If they do not and they fail to fall below the p-value, then we fail to reject the null and we cannot embrace our alternative hypothesis. If you have any questions about this, hit me up with email.